Hello, welcome to my Phys211 project. In this project, we examined the stress distribution of birefringent materials and analyzed them. So we have three phases in this experiment. First, we discussed polarization concept and we discussed it using Moses' law with two polarizers. At the second stage, we use optical rotation concept with optically active materials. And how optical rotation occurs. At the third stage, we map birefringent material between cross polarizers with different lasers, and then compare these maps and analyze the stress distribution. In the first stage, we use Moses' law. So, as you can see, when we put these two parallel to each other, the light goes on like this. But as we make them perpendicular to each other, little to no light goes to the other side. This is because Moses' law, and intensity is proportional to cosine squared function when we do that. And you can see the comparison of theoretical value we did for 11 different angles, and you can see the different theoretical values and experimental values compared in this graph. Malthus' law states that intensity across two polarizers is proportional to square root of angle between them, like between two polarizers. And as you can see, here is the theoretical and experimental comparison of the Malthus law, and there was a 37.56% error in this phase. And in the second stage, we use a optically active material as a sugar-water mixture in a beaker, and it was placed between two polarizers, and we have white source at the bottom. So in this phase, we were looking to see the different optical rotation by different wavelengths of light. So red and green and blue should be rotate by different angles theoretically, and we wanted to prove that. And you can see the video of this experiment, phase 2. As it can be seen in the video, we have optically active material at the beaker. So this phenomenon occurs because of the asymmetric molecular structure of the material, and with this asymmetric molecular structure, different wavelengths, different colors will rotate by different amount. And as you can see, we will rotate the polarizer in this video, and the observed color will change. So when we measured, the blue color was rotated by 94 degrees and green were rotated by 82 degrees. So this proves our statement that different colors will rotate by different angle. So at phase 3 of our experiment, we used a birefringent material as this one, as you can see, transparent material. So when we place it between, we have a white light source, and we place it between two polarizers. As you can see, this is the stress distribution of our material. These plus-like shape is the isoclinic fringes, and they appear dark because of the alignment in transmission axes of polarizers and principal stress distribution. And these colorful fringes are isochromatic fringes, and they show how stress distributes around the object. So when they get denser, it means that this principal stress distribution difference is higher at that point. And as you can see, at the middle of our object, we have a really dense isochromatic fringes, and this is the stress point of our material. And we use two different lasers, red and green, and we used a 9x11 stencil at this object, as you can see. and we pointed laser one by one and created a map, stress distribution map, as you can see in this video. As it can be seen, the isoclinic fringes appear on both maps, so this proves that the isoclinic fringes does not depend on wavelength, and these are the dark fringes that we saw in video with plus-like shape. So this is show that our mapping process is successful and validated with real life data. And these isoclinic fringes actually shows the stress alignment of the material. So at the end, these two maps were compared, and we have concluded the experiment with this, showing the similarities and differences between them and analyzing the stress distribution. At the end of the phase 3, to show that the stress point is where the isochromatic fringes are dense at most, here's a spoon under two colorizers, and when we break it, it will break just under that point, at stress point. And as we can see, the stress point of that spoon is at upper left corner, and as it can be seen, it breaks from there. Thanks for listening to me.